Hello students, we are going to review this guided inquiry on hybridization. Okay, so it's a relatively simple exercise asking you some questions. Some of these questions you can answer along the way based on what you have learned in the earlier section. Okay, so for question 1, they're asking about methane. So first of all, you need to understand that methane has a tetrahedral structure that is perfectly symmetrical. So it looks something like this, tetrahedral. So if you draw it the normal way, it's like that. If you want to showcase stereochemical projection, then you might want to draw the hash and the dash line like this. Okay, so this is projecting out, projecting in. If you also recall from what we discussed during tutorials, another way to look at it is that it is pointing towards the four corners of a cube. Okay, so like this, so in the middle sphere like this, so it's connecting, okay, from each of the sphere is at four corners of the cube, two on top, two below. If you perform trigonometry, okay, you will get a bond angle about 109.5 degrees. Of course, you do not need to show the proof. You can just write tetrahedral as the shape. Okay, so just write tetrahedral. Okay, and then the bond angle, quote it to be a standard 109.5. That will be sufficient. Okay, so next question asks you, are they equivalent in bond length and bond strength? Okay, so this is like a learned knowledge. So you kind of like have to learn it. Either you check it out online or it's told to you as a truth. Okay, so answer is yes. They're all the same. Okay, then you if you want to delve a little bit more into it, you can, but at least as of now, you don't need to. Yeah. So having the same bond length and bond strength has some implications. Okay, so we're going to deal with that later. Question 3, you're supposed to complete the electron in box diagram. Okay, for carbon in the ground state, some of you might not understand the term ground state. Basically, it is just the electronic configuration you would write for carbon as it is, based on Hund's rule, okay, and Pauli exclusion principle. So if you look at carbon, its electronic configuration is 1s2, 2s2, 2p2, right? Yep, so valence electronic configuration, the 2s subshell is being filled, and then the 2p singly occupied. Okay, one of it is empty. So question 4, based on your answer in question 3, how many covalent bonds can carbon form bonds with hydrogen atom? So you'll notice that there are only 2 unpaired electrons in the 2p subshell. So if I'm going to form a bond with hydrogen, I can only utilize these 2. Yeah, but you obviously know that this is not the case, right? Because methane forms 4 bonds. So in this case, this ground state model where carbon undergoes reaction with hydrogen is probably not the correct one. Okay, but anyway, when you're answering this question, just answer it as it is. So the answer here is 2. Okay, and then based on this, what is the okay, I think that's about it. I shouldn't go too much into details, so I'll just move on. Okay, so to explain the 4 covalent bonds, we may propose that the electrons are excited. Okay, so what this is going to happen is that the 2s electrons undergo excitations during chemical reaction. Of course, this is just a postulate. It may not be the truth. Okay, so so remember that all the models we learn are humans' attempts to explain what happens in reality. Yeah, so until a new model is being presented and show that the older models are wrong, or the older models has certain exceptions, etc., or certain constraints. Yeah, if not, the model that is given to you should be able to predict most of the situation or scenarios. Okay, so that is something you need to be aware of, right? So we're going to propose an excitation model where one of the electrons in 2s is being excited, okay, and to that in 2p. So all singly occupied, okay, and question 5 is asking you what is the bond angle between the 2p orbitals in carbon. You know that the p subshells has 3 orbitals. They orientate themselves along the axis, y-axis, and the z-axis. Okay, it looks like a figure of 8. So if we look at a py, so if this is x, this is y, so a py will look like this. Okay, and then this is z. Right, so the angle, okay, so if I'm going to draw px in, it will look like this. So the angle is actually 90 degrees. Okay, so this should be clear cut. Then based on your answers in question 1 to question 5, suggest evidences to show that a new model is required to describe the shape of methane. So again here, they ask you for your suggestion. Why is it that a new model is needed? So there are many reasons you can use to actually explain this. Okay, so number 1 is methane is tetrahedral in shape, right? If it's tetrahedral, right, that means that this model must be wrong, because if I'm going to have a bonding model involving the current one, the current carbon, excited carbon utilizes 2s and 2p, right? I am not going to get a bond angle of 109.5. Yeah, so I probably will get something very close to an octahedral, but not really an octahedral, because the H will just form bonds with the carbon in the middle like this, right? And then it looks a bit weird, I know, but I mean, that's the best way we can try to describe what's happening. And then maybe another H is just somewhere in this space, something like that. Yeah, so you're not going to get a perfect tetrahedral orientation around the central carbon. Okay, you're going to get some weird shapes, right? So that's number 1. Then number 2 is that I'm going to form 4 sigma bonds, right? Now, based on your understanding from question 2, methane, all the CH bond in methane should have the same bond strength and therefore the bond length. Yeah, in our case here, because the 2s orbital is closer to the nucleus and the 2p on the average electrons further away from the nucleus as compared to 2s, you're going to expect something like a 2, or rather something like 3 long bonds and 1 shorter bonds. But this is not the case in methane. So because of that, I will need to utilize a newer model or another model to explain the shape of methane, and therefore to explain many things about carbon in general. And the idea of hybridization actually helps to fill that gap. And this hybridization concept, it's quite prevalent in modern organic chemistry, because a lot of the ideas, you can actually use it to explain a lot of organic phenomenon. Yeah, so it's actually very useful. Okay, so you have a whole paragraph here trying to explain what hybridization is. So basically, it's a mixing of orbitals. So if I have 1, 2s, and 3 sets of 2p orbitals mixes together, you're going to end up with 4 sets of sp3 hybrid orbitals. Okay, so 1 plus 3 is 4, so we end up with 4. So that's what we call the conservation of orbitals. Okay, if I'm only utilizing 1 2s orbital and 2p orbital, then I'm going to end up with 3 hybrid orbitals. That's called sp2. And then the remaining p orbital will be unhybridized. This particular unhybridized p orbital is important because it is going to be used to form what we call the pi bond, which you might have read in the earlier section. Okay, then so that's a characteristic of the hybrid orbitals here. Okay, so so described to you. Arrangement of the orbitals around the central carbon atom sort of utilizes what you learn in VS EPR theory. So if I have 2 electron groups, right, I'm going to end up with linear. 3 will be trigonoplanar, and then 4 will be tetrahedral. Okay, so if it's sp3, there will not be any unhybridized p orbitals. Okay, the hybrid orbital have this particular shape, a big lobed, okay, and a small one. So you need to learn how to draw it. Okay, and then for question 8, it asks you to sketch labeled diagrams to show how the shape and arrangement of hybrid orbitals around sp, sp2, sp3 environment. Okay, they ask you to include the unhybridized p orbital. Okay, so I'm going to start off with sp. Okay, I might not draw everything. Okay, what I'm going to do is I'm just going to draw a dashed line. Okay, so maybe I should use a ruler. Okay, maybe not a ruler, but okay, not eraser. Let's see what I'm going to do. Okay, I want to draw a dotted line. Okay, maybe not red. I'm going to choose a different color. Okay, green. Okay, you don't include this line you're drawing. Okay, actually this should be a dotted line. Let me see how to get a dotted line out. Okay. Maybe I'll try one more time. Okay, right. So I got it out. Gonna erase this. Right. Okay. This actually helps you to sketch. Okay. So so around here, I'm just going to draw in the hybrid orbital like this. Okay. Then we'll draw in another one like this. Okay. 180 degrees apart. Okay. I hope that is okay. So remember that hybrid orbitals, SP, they are linear in geometry around the central carbon. Okay. Then what I'm going to do is I'm going to use a different color, okay, to show the px or the py. It really depends. So if let's say you want to label this as x, for example, okay, just random example, right? Then your unhybridized orbital will be py, okay, and then another one, if you want to use a different color, it will be the, oops, sorry, not so nice, okay, it will be the pz. Okay, I hope that's all right. Color coding actually helps a lot in the way you showcase the drawing. So whenever possible, try to color code using maybe different shades of blue, or maybe sometimes some in black ink, some in blue ink, if you can. Okay, I mean, you don't have to, but if you can, because I think it helps to give some clarity. Okay, next I'm going to showcase to you how to do tetrahedral. I think I showed that in the classroom before. Again, you use dotted lines to show some of these. Okay, I think it helps. Okay, like this. Okay, then you draw your hybrid orbitals. So again, you draw it. Oops, sorry, can't do it like this. Okay, right. Okay, again, one big loop. Oops. Okay, one big loop, one small one. Okay, and then a big one and a small one, a big one and a small one, and then a big one and a small one. Okay. Okay. My apologies, because if I draw on screen, it's not so nice. Yeah, but if you draw on paper, I think you can definitely do a much better job. Then if you super hit the dotted line, which you should have done in using pencil, just erase it off. If you get what I'm trying to say. Yeah, that is probably the answer you're going to give. But if you are okay with it, just leave it around. Yeah, I mean, it helps to guide you in your drawing. Okay, yep. So I might as well just draw for SP2. Okay, so for SP2, again, relatively straightforward. So again, I need to draw trigonal planar geometry to the best of my ability. Okay, planar geometry, something like this. Okay, and then again, big loop, small loop, big loop, small loop, big loop, small loop. Okay, then the unhybridized P will be like this. Yeah, so normally the XY plane is here, so we just label this as PZ. Okay, it's really up to you. I know the shape is a bit out, so maybe I should draw it a little bit smaller, but I mean, if I'm not so strict, yeah, like this will do. Okay, yep. So so remember that try to use dotted lines to guide you in your drawing. It actually helps to make your drawing a little bit neater. Okay, of course, if you're running out of time, then that's another matter. But usually, if you try to use dotted lines to guide you in your drawing, your answers will be a lot cleaner. Right, okay. So we're going to end off with exercises. Okay, so the exercises here, so question 1, bond length in propyne differ from those which might be expected. Okay, so the typical carbon-carbon bond length in ethane is 0.154 nanometers. That in ethine is 0.120. Single bond in propyne, however, is 0.146. Okay, so this is a single bond. Okay, so they ask you which one helps to explain the C2C3 bond length in propyne, right? Then A say it has a partial sp2 character. this thing has some flaw because what is a partial sp2 character? So it's a wrong concept. Okay, so it's wrong. B, it's an sp-sp3 overlap. Is it true? Answer is yes, because this is sp hybridized. This is sp3. Yeah, but this does not help you explain why it is shorter than a typical single bond ethane, because a typical single bond ethane, right, is sp3 sp3. Correct? Yeah, so this is sp sp3. So sp sp3 seems to be a bit shorter. Okay, maybe 20% shorter than 10% shorter than sp3 sp3. Why is that the case? So again, possibly it's the answer, but we need to explore the rest of the option. Okay, C, the sp3 bonding is put shorter by a p pi. Oh, so this is nonsense. The one is wrong. Okay, so it's wrong. Donkey, the electrons in C3 carbon atoms are attracted towards the pi bond between C1 and C2. So again, there's no such concept. Okay, there's no such thing as if I have a pi bond, electrons will be attracted. Yeah. So options A, C, D are incorrect. Option B is the correct statement, but it doesn't help you to explain unless you unpack why is it that sp3 overlap makes a shorter bond. So from here, we're going to unpack it a little bit. We are looking at percentage of S character. Okay, so sp has 50% of S character because it's made up of one S and one P. So out of the two orbitals, one of it is S, so 50% S character. sp3 percentage of S character is 25%. So out of the four orbitals, one of them is an S orbital. So because of that, the percentage of S character is 25%. Yeah, why is percentage of S character an important factor here? Because percentage of S character gives you an indication, okay, of on the average, the electron density in the hybrid orbital, is it closer to the nucleus or slightly further away from the nucleus? Yeah, remember that electrons in the S orbital tends to be closer to the nucleus as compared to that in the p orbital. So therefore, you can draw a conclusion here. The greater the percentage of S character, yeah, on the average, the electron densities in a hybrid orbital, in this case the sp hybrid orbital, will be closer to the nucleus as compared to that in the sp3 hybrid orbitals. Yeah, and since the electron density in the sp hybrid orbital is closer to the nucleus, that also means that when they form a bond, the bond overlap, or the electrons shared between the two carbon, okay, in this case sp and sp3, okay, will be slightly closer to the nucleus because it's more strongly attracted as compared to that in sp3 sp3, okay, in ethane. Yeah, so option B statement is a starting statement to help you to explain why the bond is shorter, but they did not complete it with the explanation. Yeah, so if they can complete it with the explanation, it will be helpful, but since this is MCQ, there is no need to, so I think it is good enough to be chosen as the correct option. Okay, now question 2, gonna look at Lewis structure, okay, and state of hybridization state of a central atom. Okay, so again, this is formaldehyde. Okay, it's something you avoid in newly renovated houses. Okay, it's toxic. So if I draw the Lewis structure, it looks like this. Okay, so you notice that how do you determine the hybridization state? There's a simple way. You look at the number of pi bonds. Okay, you notice that for methane, right, the central carbon, 4 single bond, no pi bond, so it's sp3. Okay, for ethene, okay, ethene looks like this. The carbon, 3 single bond, one pi bond, so that means it's sp2. Because why is it sp2? Because you need, whenever you form a pi bond, you need one unhybridized p orbital. Okay, yeah, so you can predict the hybridization state by looking at the number of pi bonds the carbon has. So in this case, formaldehyde, the carbon has 1 pi bond, so therefore the hybridization state must be sp2. because it needs to utilize one of the p orbital to form the pi bond. Okay, this is hydrogen cyanide. It looks like this. Okay, the carbon forms 2 pi bonds. Right, I'm going to highlight the pi bonds to you. These are the pi bonds. Yeah, so again, it has 2 sigma bonds, 2 pi bonds. So that means that in order to form the 2 pi bonds, it must have 2 unhybridized p orbital. Okay, hybridized p orbital. Yeah, so if it has 2 unhybridized p orbital, hybridization state of the carbon must be sp, because it only utilizes one s and one of the p orbital to form the hybrid orbitals. Okay, so that's how you can tell. Yeah, so again, looking at the number of pi bonds helps greatly. Now, C is a bit harder. It's hydrogen peroxide. It looks like this. At first glance, maybe no hybridization, because hybridization seems to be the concept that applies only to carbon. That statement is partially right, partially wrong. It really depends on how you look at the world. I mean, it's not so straightforward sometimes. Maybe I should say hybridization as a concept originated from carbon, or we want to understand more about carbon. Then as organic chemistry progresses, okay, it sort of includes nitrogen and oxygen, okay, in the discussion. Yeah, so if you want to, you can actually invoke hybridization concept for nitrogen and oxygen if you want. But if you do not need to, then you don't have to. So if let's say we want to invoke hybridization for hydrogen peroxide, what shall we do? Yeah, we just do what we need to do directly. So oxygen electronic configuration is 1s2, 2s2, 2p4. Okay, so if it's going to undergo hybridization, so this 2s, this 2p, right? What's going to happen is that it will form 4 sets of sp3 hybrid orbitals, right? 2 of the hybrid orbitals are filled. Okay, the other 2 are unpaired electrons. So can you sort of visualize that these are the 2 filled hybrid orbitals? Okay, then these 2 unpaired electrons are used to form these 2 sigma bonds. Yeah, so basically the overlap here, over here, right, is a sp3 1s overlap to form the sigma bond. It's a sigma overlap. Okay, sigma overlap. Okay, so that is like we're gonna pull to the extreme, invoking hybridization to explain hydrogen peroxide. Well, you don't have to. You only do that when you're asked to, right? Usually we don't use it. Yeah, then sometimes if you do a little bit of organic chemistry where the structure involved oxygen and nitrogen as part of the structure, sometimes you need to invoke it in your explanation to help you understand certain things. Sometimes you have to, sometimes you don't have to. It really depends. In organic chemistry, you do not need to invoke hybridization in most cases. Yep, so you have to be a little bit more agile, okay, when you invoke concepts to explain. Other than that, I think it's fine. I'm not going to go through food for thoughts because don't really like it involving d orbitals, because again, hybridization is best to be kept only within carbon. If it involved other shapes, then we might not. I mean, it might not reflect reality so closely. Yeah, okay. But of course, if you want to, you can just base it on what you learn under hybridization, and then I mean what you learn under sp3, and then you extrapolate and understand what happens when you're dealing with trigonal, bipyramidal, and octahedral. So in this case, dsp3, that will be 5, right? Just count the total, and then the other will be 6. And then of course here you probably need 1s, and then 3 sets of p, and then 1 of the d, and then this is 1s, 3 sets of p, and 2 d's, right? Okay, and of course the angle here will be all 90 degrees. Okay, because we are looking at octahedral like this. Okay, and then the other one will be trigonal bipyramidal, that will be 90 degrees for the axial. Okay, and then 120 for equatorial. Okay, I won't go too much into details because again, not very keen in invoking hybridization beyond uh, tetrahedral geometry. Okay, I think that's it. Thank you for listening. I hope it brings you some additional insights. Then, yeah, if you have other issues, feel free to address them in the tutorial.